So let's talk about the F distribution. So we've looked at the normal distribution, we've looked at the chi-squared distribution. So now we have another distribution called the F distribution. So it's named after Sir Ronald Fisher. He's also a very popular statistician. He did the Fisher's test. There's some other stuff that he's done. So he was one of those grandfathers of statistics. So for this one, there's two sets of degrees of freedom, one for the numerator and one for the denominator. So when you write the F distribution, the number of degrees of freedom for the numerator is 4, and the numerator for the degrees of freedom of the denominator is 10. And this is just an example. The cool thing is when you use the software for this, it gives it to you anyway, and you don't have to worry about finding it yourself. All right. So one way ANOVAs and even regressions, I didn't talk about this in the regression video because it's not hugely important for intro level stats, is it makes a table for you. So this source of variation factor between, it's comparing the means to one another. The error within means it looks at each sample individually. And then you get the sum of the squares, and then the degrees of freedom, the mean squared, and then the F value at the end over here, if you look where F is. I'm not going to go into what each one means, but just know that basically what we're doing in this test is we're looking at the means and the variances among the groups as they look. Think of groups, you're comparing samples to each other, and then you're comparing the sample to itself. You're seeing, is it normal? How far away is that variation? And those are the things we need to be mindful of when we run this test. So to calculate the F ratio, you have two estimations of the variance. So like I just said before, the variance between the samples. So all that means is I'm trying to see if samples are different sizes, the variance is weighted accordingly to the different sizes. And then the variance within the samples, so that's the sample itself. And if it's a different sample size, it's going to weight it accordingly. The SS between is the sum of squares that represent the variation among the different samples, and the SS within is the sum of squares that represents the variation within the samples, and that's due by chance. So you find the sum of squares, you add them together, and then you come up with the mean square, and the mean square is the variance between the groups, and the mean square within is the variance within the groups. And if you do the mean squared between divided by the mean square within, you get the F value. And you're like, please don't make me do this by hand. And you'll never, ever, ever have to do this by hand. There's a website we use, and it is so helpful. So please don't feel like you ever have to do this by hand. I just want you to kind of see the takeaway of this is when you're comparing samples, you've got to look at each of them compared to each other, and then each of them individually. Okay, so let's talk about the F distribution. The curve is not symmetric, but it's skewed to the right. There is a different curve for each set of degrees of freedom. If you look in certain textbooks, the back tables of some of these statistical textbooks have like over 100 F tables. We're not going to worry about that because the wonderful thing is the p-value helps us with this. The F statistic is greater than or equal to 0. As the degrees of freedom for the numerator and for the denominator get larger, the curve approximates the normal distribution. Other uses for the F distribution include comparisons of two variance, two-way analysis of variance, and two-way analysis of variance is way beyond what we're doing, but you can go up to four-way, eight-way. You can make enormous ANOVAs. Okay, and here's this shows, if you see this F value on the left, you see that it's F with a degrees of freedom of 10 and 25, where the one on the right is an F with 40 and 40. So as you see, they tend to take different shapes. And again, like we said in the last one, as the degrees of freedom increase, it approximates the normal curve. And that is kind of starting to become a normal curve.